Hello guys, in this video we are going to discuss the solution of the problem generalized Fibonacci numbers. So let us look at the problem statement. The problem statement says that consider the generalized Fibonacci number g which is dependent on a, b and c as follows, where g1 and g2 are equals to 1 and other number n gn is given by this expression where gn is equals to a times gn minus 1 plus b times gn minus 2 plus c. So given these constraints, we have to determine gn mod n for a given n. So let us try to understand the problem statement with the help of an example. So here a, b, c, n and m are given to us and these are the values, and the nth term is what we would like to find out. Here n is equals to 3, so the nth term g3 will be equals to 9. So 9 modulo 5 is what we need to return, in which case it is 4, and that is what we are returning over here. So that's about the problem statement, folks. Now let us discuss the optimal solution for this problem. So here the idea behind the optimal solution is basically to perform matrix multiplication. So let us discuss how this Fibonacci sequence or a generalized Fibonacci sequence which is given to us, transform it to a matrix and then use matrix multiplication in order to achieve our answer. G1 which is given to us is 1, G2 which is given to us is 1. Sequence which is given to us is Gn is equals to a times g of n minus 1 plus b times g of n minus 2 plus c. So this is what the equation which is given to us. So let us first represent this equation in matrix format. So in matrix, the equation we could say that the equation Gn is equals to, so what we have to do is a, b, 1, and then this has to be multiplied with g of n minus 1, g of n minus 2 and c. This is how we could rewrite the equation in matrix format. So now let us work with some example in order to see if we can achieve optimization via matrix multiplication. So let us take the first example where n is equals to 3. So here we would like to compute G3. Well, G3 is equals to A, B, 1, and let's have it over here. So this is G2, and G2 as we know is equals to 1, and this is equals to G1 which we know equals to 1, and this remains C. Now let's move forward. So let's go ahead and compute for n is equals to 4. So now G4 is equals to, we can rewrite it as, and this is equals to G3, G2 and C. But as we are moving forward, we can say that this sort of representation in matrix format is not giving us a way by which we will be able to solve this problem in an optimal way. What I mean to say is, if you go ahead and try to compute G3, we need to perform this multiplication. Similarly, if you go ahead and try to compute G4, we will have to compute this matrix multiplication. Now let us see if we could do something with this matrix. We could probably add few rows over here and see if with those matrices whether we will be able to solve this problem optimally or not. So this is the matrix representation of the equation we have. So now what we are going to do is, we are going to say that let us represent g of n minus 1 also. So in order to represent g of n minus 1, what we are going to do is, so this, if you see, this gives me g of n, and we want to know g of n minus 1. So this is g of n minus 1. So in order to get g of n minus 1, all I have to do is, I just need to set this particular index to 1 and the remaining two could be a 0. So if we go ahead and now let's say the matrix is this. So if you go ahead and compute for the second row, these two terms will be 0 and the first term will be relevant, and that first term is g of n minus 1. That is what we need. And similarly, if you go ahead and try to make this as C, so let us make it as C. So if you want to evaluate the third row to C, we have to set this last element of the matrix as 1 and the rest of the element as 0. That is how if you multiply the last row with the column we will get C. So now with little bit of addition of rows and columns in the matrix, our matrix now looks something like this, or the equation we could generalize it in this format via matrix. Now let us work with this matrix equation which we have in with some example and try to see if we have optimized the problem or not. So let's take an example where n is equals to 3. So here when n is equals to 3, we would like to find out G3, G2 and C, and this is equals to, we can write it down as A, B, 1, and here this is G of n minus 1. So remember n is equals to 3, so this will be G2, this will be G1 and this will be C. After putting n is equals to 3, the equation got transformed into this, and let us call this as equation 1. Now let's work with when n is equals to 4. So in this equation, now let us go ahead and put n is equals to 4 and let us see how this gets transformed to. So we want to compute G4, G3 and C. So this is equals to, so on putting n is equals to 4, our generic equation got transformed into this format. So now if you focus on this matrix, this is a matrix which we have computed before. So if you see this, if you refer to our equation 1, this is what we have computed. So now let us go ahead and use the value. So the equation got transformed into this equation. Now because of this, we can see that this is something which is getting repeated. So what we can say that is this particular equation we could rewrite it as, so here we can see the optimization, or in order to compute a value we have to perform this matrix multi. So now let's go ahead and proceed further and work with when n is equals to 5. So the values of G5, G3 and C will be equals to this value. I'm not going to do the entire computation here, but you can go ahead and do it on your own in order to see that when n is equals to 5, the equation can be rewritten in this way. So from here we can deduce a generalized equation, which is if we want to compute the value of Gn, then Gn will be equals to, sorry guys, this is 4. There is a correction over here. Please note this is 4. So in this way, we will be able to generalize the equation. So in order to find the value of Gn minus 1 and C, we have to take this base matrix with us. So let us call this matrix as our base matrix. We have to take our base matrix and we need to compute base matrix to the power n minus 2, and then towards the end the resultant value is what we are going to multiply it with G2, G1 and C. Please note G2, G1 is equals to 1, so essentially this will be translated into 1, 1 and C. So that's the general idea folks. In order to compute Gn, we need to perform exponentiation of base matrix to the power of n minus 2. Once we have performed the exponentiation of base matrix, we need to multiply it with 1, 1 and C in order to get our answer. So now let us go ahead and discuss how we would be able to perform exponentiation in an optimal way. So in order to perform exponentiation in an optimal way, there is one little concept which we need to understand, which is if you multiply any matrix with its identity, then the resultant matrix is matrix itself. So this is one concept which we'll be using in our explanation. So in order to discuss the optimal exponentiation, let us take an example and let us say over here we want to perform base matrix to the power 13. Now one way to perform base matrix to the power 13 is essentially you go ahead and perform 13 multiplication, and this is essentially a naive algorithm or a brute force solution which is going to take order of n times, where n is equals to 13. Another way or an optimal way of doing it is we will start with our base matrix, and then what we are going to do is we are going to go ahead and compute bm square. So bm square can be computed just by squaring bm itself. Similarly, once we have bm square, rather than computing bm cube and so on, what we are going to do is we are just going to go ahead and square bm square and we will get bm4. Similarly, we are going to go ahead and square bm8. So now given this, which is bm square, bm4 and bm to the power 8, 13, bm to the power 13 can be constructed by bm to the power 8 into bm to the power 4 into bm to the power 1, right? So we see here, even though we are computing bm square, but we are not using it. But how do I know which one to take and which one not to take, right? So in order to do that, let us go ahead and represent 13 in its binary format. So let's say 13 is this. The binary representation of 13 will be, so this is the binary representation of 13. So as you can see, this is 0th, first, second, and third. So the bits which are set, the corresponding value or the corresponding exponentiation is what we are taking. So if you see here, 2 to the power 3 is 8, and this is what we are taking over here. 2 to the power 2 is 4, and this is what we are taking here. 2 to the power 0 is 1, and this is what we are taking over here. And see, once it is 0, then we are excluding that. So 1, which is 2 to the power 1, which is equals to 2. So this we are excluding it. So an optimal way, and let's just briefly discuss the code for this. The optimal way to do this will be, let us say we will have something known as count, and please note we need to compare base matrix to the power n minus 2 from the equation. If you could recall, let me just scroll up. So here if you see, we wanted to compute base matrix to the power n minus 2. So now we want to compute base matrix to the power n minus 2. So what we are going to do is, we are going to set count is equals to n by 2. And now we are going to iterate on the bits of count. So we are going to say while count is greater than 0, and now let us iterate on the bit. So now what we are going to check is, we are going to check if the bit is set to 1, right? If the bit is set to 1, so this will give me the least significant bit. If the least significant bit is set to 1, then that squared matrix is what we want to take. Okay, so let us say there is a squared matrix, and this squared matrix we are initially setting it to BM matrix, base matrix. So let me just rewrite it over here. So base matrix will be equals to this. Now what we are going to do is, we'll have a variable where we will set squared matrix is equals to BM, right? 2 to the power 0 is what I am saying over here. And let us say we will have something called as a result matrix, and result matrix is initial value of result matrix is an identity. So the identity of 3 by 3. So this is the identity of 3 by 3. This is my initial value of result matrix. If the bit is set, then that particular squared matrix which we have computed so far, which we want to include in our result matrix. So the result matrix will be equals to the squared which we have done so far into a result matrix. Otherwise, we will go ahead and we need to compute the squared matrix all the time. So the squared matrix will be equals to squared matrix into Sm, right? Please note, initially the squared matrix is Bm. Okay, I'll just go work with an example in order to explain this concept, because I think this is little bit confusing. And once we have done that, then we are going to shift our bit by 1. So let me just work with an example in order to explain this. So please note this, base matrix is this, squared matrix is equals to BM matrix, and result matrix is an identity. So let us say over here n is equals to 15. So our count will be equals to 13, and we want to compute BM to the power 13. Now let us represent 13 into binary. So this is the binary representation of 13. Now what we are checking is, we are checking whether the least significant bit is set to 1. So if the least significant bit is set to 1, then we are going to say that our result matrix is equals to Sm into result matrix. So our Sm is equals to Bm for now, and then Bm into Rs is our identity matrix. So for this particular case, our result matrix will be equals to our base matrix. Then we have gone ahead and computed Sm equals to Sm into Sm, which is essentially Sm is equals to Bm square so far, right? Now, and after that we have shifted it by 1. So now after shifting, this becomes 1, 1 and 0. Now at this time this is equals to 0. Now since the least significant bit is 0, then the result matrix will not be altered, and we will go ahead and compute SM again. So at this position, when we are computing SM again, then SM will becomes equals to SM into SM, which is equals to BM to the power 4. Now BM to the power 4 is there, and then we have left shifted. Then we have right shifted. So now this becomes equals to 1 and 1. Now here the least significant bit is 1. Since the least significant bit is 1, then the result matrix will be updated, and result matrix will be updated as squared matrix, which is equals to BM to the power 4 into result matrix. Please note result matrix was BM. So this is the value of our result matrix. After doing so, we again go ahead and computed SM. So this time the SM will be equals to BM to the power 8. And then we have right shift. Then we will do a right shift. So now this is equals to 1. And again we saw that the least significant bit is set to 1, because of which we will go ahead and include BM to the power 8 in our exponentiation. So the result matrix is now this: BM into BM to the power 4 into BM to the power 8. After that, we will go ahead and shift it by 1. So this becomes equals to 0. So this is what we wanted, right? Result matrix is 8, 4 and 1, which is equals to 13. So this is what we wanted to compute. And once we have our result matrix, we will just go ahead and perform the last matrix multiplication which we wanted to do. Please note, by exponentiation, we have just computed base matrix. So this base matrix needs to be multiplied with this 1, 1 and C. And that is something which we will do and get our result. So that's about the explanation, folks. Now let's go ahead and see how we can code this. So I've already coded this, folks, and the code is something like this. If n is equals to 1 or 2, then we need to return 1 modulo m. If n is equals to 3, then we know that the value will be equals to a plus b plus c modulo m. Otherwise, we will have a base matrix with us, which is this. And then we will have our result matrix, which will be equals to identity. And then we have a squared matrix, and then count equals to, we are setting count equals to n minus 2. And then we are doing the exponentiation. So this is the logic for exponentiation, folks, which we have discussed. So this is the last part, and let me just switch back over here in order to explain this. So this is what we want to do. So this is the first row. So remember, this is what we need. We are not interested in any other term. This is the term which we are interested in, which is Gn. And in order to get Gn, we just have to take the first row and the first column of this matrix, and we need to multiply it and get our answer. So which will be equals to the value present over here plus the value present over here plus C times the value present over here. So that is what I have done over there. So as you can see, result matrix 0th first, and then C times the second position. So that's about the code, folks. Now let us go ahead and submit our solution. So our solution got accepted. That is all from this video, folks. In case if you have any question or comment regarding this video, please feel free to use the comment section and I'll try to address them. Thank you.